Welcome to the course Electronic System Design. In the last lecture we discussed that electronic systems has certain design stages which are very common to all the industries working in the electronic design domain. There are mainly 6 design stages, and we discussed in the last lecture that we have something called device design stage, where we develop a device which is a MOS transistor in general case. This MOS has 3 terminals: source, gate and drain. Of course, there are other terminals which we are not considering. So, this device is first developed in the very first design stage for its performance, just like the FT and Fmax and the R-on and drain current. There are certain parameters for which this device is optimized in the first design stage, and then after developing this device, we measure the performance of this device and we try to model it using some equations, which is a MOSFET equation for drain current, ID equal to half mu n C ox W by L VGS minus VT whole square. Once we put these equations to mimic the actual behavior of this device, this step is called the modeling or the device modeling. These models are put together in a file, something called library, and these libraries are generally distributed by these foundries who are making these devices. This library is given to all the industries which are working in the next stage, which is called circuit design stage. In circuit design, we take these libraries or the models of MOSFETs and we start making the circuits and measure the performance. If performance is adequate, then we make the layout of the circuits. So, this is the circuit design stage, and in the gate level design stage we shift to the Verilog or VHDL based languages, because SPICE or the BSIM based SPICE simulations, they are very complex in time. So, to decrease the simulation time and design time, we switch to digital languages, which is Verilog and VHDL. That is called the gate level design stage. Today we will discuss the next stage from this gate level design stage. This new stage is called the module level design stage. So, let us discuss the module stage. This module level design stage, we design and simulate functional modules like from the HDL. These functional modules are something like ALUs, the arithmetic logical unit, or full adders, subtractors, multipliers, all those modules we design in this stage. And in this stage, we generally do not draw individual layouts, we do it using CAD softwares. So, there is a auto generate of layout from the complete module. using synthesis tool. So in this design stage, we design and simulate functional modules which are complete in itself. For example, a full adder circuit. This is a full adder which can take a carry and two arguments and provide the addition of those input parameters. In module level design, we do it using HDLs, which are hardware description languages. Then we auto generate the layout of the circuit, which is very different than the other modules, the previous modules. In previous modules, for example, in circuit design, we design an inverter and draw the layout generally manually. Some engineers sit together and they draw the layout of the circuit of inverter or NAND gate by hand. But here in module level design, we are talking about multiple transistors together, typically more than 100 or 500 transistors will come together to make a complete circuit. At this time, drawing the layout manually for all 500 transistors is not advantageous. If it is possible, it is not advantageous. So we use HDLs. There is a separate module which is called synthesis. In that, we can auto generate the layout for these 500 transistors or even more. So in this module, we automatically generate the layout, which is not drawn generally by hand like previous stages. So for example, we have a circuit which is a full adder circuit here. So full adder circuit looks something like this. This is input X, this is input Y, So this is a typical circuit of a full adder which takes two inputs as input X and input Y, and there is a previous carry from the previous stage which is carry in. These are the three inputs to this circuit, and it produces two outputs. One is the sum of these input and input X and input Y along with the carry, and there is a generation of carry for the next stage. So this is a complete full adder circuit. Let's write a HDL code for this circuit, which looks something like this. We first define a module full adder which has all input and output definitions: input underscore X, input underscore Y, carry in, sum out, and carry out. So this is the module initiation. Then we define input x as input. Similarly, we define output signals as sum underscore out. So these are input and output definitions. Then we define wires for connecting the blocks. Wire w underscore sum 1, wire w underscore carry 1, and wire w underscore carry 2. And then we assign carry underscore out is equal to w underscore carry 1, w underscore carry 2. And then we instantiate two half adders to make the complete circuit. So this is a comment in the HDL, and then we instantiate two half adders. First is half underscore adder u1 underscore half adder dot in x in underscore x dot in y in underscore y dot out underscore sum So this is the first instance of half adder. Similarly, we will have a second instance u2 underscore half adder which is dot in underscore x w underscore sum 1 and then we close this second instance, and then we close the entire module, which is the statement end module. So here is the sample HDL code which is written in Verilog language. We have a module which is defined as full adder, which has 3 inputs and 2 outputs. First we define the parameters which should define as a input or an output. So there is a command input to define as a input type and output as a output type. Then we define some wires which will be used to connect these two different modules together, and then we call two instances of a single module which is called half adder u1 underscore half underscore adder and then u2 underscore half underscore adder. So these are two instances of the same modules which is half adder, here specified by this. So this is one half adder and this is the other half adder. So these two half adders are then joined together using these wire statements in this way, so that it produce some output and carry output, which is a complete full adder circuit. So this is how we make a complete modules. Even this is a very simple example, but we can make a very big module by using the Verilog HDLs. Once we design these modules, then we can auto generate the layout of this complete circuit using the tool called synthesis. We just have to provide this full circuit to the synthesis tool, and the layout, which is the actual representation of the structure on the mask or on the silicon, that layout will be auto populated by the synthesis tool. So this is the fourth module, fourth design stage, where this is a module level design stage. In the next design stage, we have IC design stage. So in this IC design stage, we first produce all the building blocks using module level design. We put together all the modules, whatever is needed for our functional chip. For example, we are developing a processor for our mobile phone or for our laptop. Then this processor might have some RAM, which is for the memory. See, it can have some IO circuits, it can have some core circuits to do for various functions. It may have multipliers, adders, subtractors. So we list down all the modules which we need to make, and in the module design stage we bring all these modules together to form a complete kind of functional modules or functional layout of all the modules. In the IC design stage, we take up all this layout, is a complete big file. We take up this layout and we go back to the foundry who developed that MOS transistor in the first design stage, which is a device design stage. We go to the foundry and give them our layout files and ask them to produce the silicon, the IC design for our actual design. So in this IC design stage, the foundry will take the layout and process it using the CMOS fabrication process, and there generally there is a it's a wafer which is involved. On wafer, foundry is going to produce our IC, the chip we call it. This wafer is generally a 12-inch wafer currently being used in the IC industry. So this is a silicon wafer. It's a circular silicon wafer. There is a cut on one side for alignment, and on this wafer generally ICs are produced like this. They are all same in size. So each one of this square block is a complete IC, and when we take it out, we cut this wafer. This comes out as a complete IC, which may be a complete processor. It may have the core circuits, it may have memory, it will have IOs, it will have controllers, etc. So in this IC design stage, we start up with a wafer which is generally a 12-inch wafer, and we fabricate the IC designed by the designers. These ICs are generally in a rectangular or a square shape. These ICs are small in size, typically maximum 1 centimeter to 1 centimeter, and we produced many of the ICs, in fact more than hundreds of the ICs on a single wafer, which is a 12-inch wafer. Once we produce these ICs, then we, using the laser cutter, we cut down all this wafer into a single pieces. Each piece is a complete IC, or we call it the chip. So this chip is a piece of silicon where we have fabricated all the modules whatever is needed for our design. So this is the IC design stage. In this design, we have complete functional design, various analog and digital modules. Various analog and digital modules. Timing and power constraints taken from circuit design stage. We synthesize complete function using HDLs. and then place and route for minimum space and power density. So once we fabricate the IC on the complete silicon, this chip, a single chip, contains complete functional designs which can include multiple analog and digital blocks. Timing and power constraints are taken from circuit design stage. So generally there are constraints for timing and power. For example, one module is generating too much of power dissipation. So we generally want to distribute all these kind of modules which are heavy on power dissipation. We try to distribute it evenly so that not a single corner of a chip get heats up because of the crowding of these kind of modules. So we generally take all these constraints from circuit design stage, which is the second design stage in our complete electronic design. We synthesize complete function using HDLs now, because when we are talking about a complete chip, we are talking about millions of transistors functioning together. Generating the layout for millions of transistors by hand is not possible. So we generally generate the layout using the synthesis tool, which synthesize using the HDLs. Then there are other constraints, for example, place and route for minimum space and power density. As I said, if 2 or 3 modules are generating too much of power dissipation, we want to keep them away so that they are not producing all the power in a very confined space, which can degrade the device performance. So there are place and route constraints which we need to take care during the IC design stage. So once we have this IC, this chip fabricated by the foundry, this will be delivered to us. Then this chip is very fragile. We cannot even touch it by bare hands. So we take this chip and put it in a protective enclosure which is called the package. So package is a metallic casing usually made up of ceramics. We put this chip on the package and we connect the outer periphery, the pads on the chip, to the pin of the packages. So these packages provide multiple functions. One is the mechanical strength to the chip. The other is the power dissipation. They are made up of ceramic, which is a good conductor of heat. So any heat generated by the chip inside, that will be immediately taken away from the chip to the surroundings, so that the chip does not heat up and it can work. So the packages are generally made up of ceramic, and there are many kinds of packages available in the market depending upon our requirements. There are DIP package, dual inline package. We have SOIC, we have QFN, we have QFP. There are ball grid arrays. There are many kind of packages available in the market depending upon the number of pins, and depending upon the density we can choose any one of these packages. So there are multiple packages involved, and after this IC design stage we end up with a complete IC which is packaged in a ceramic casing. Let us say we have a DIP package. So DIP package looks something like this. We have a black structure. This is a ceramic casing and it has pins coming out, metallic pins. They come out like this. So, this is a dual inline package or DIP we call it. So, at the end of this IC design stage, we fabricate the IC and put it in a protective casing which is called the package. So, after package, we have a complete IC which is able to perform certain function which we have designed it for. For example, this is a display driver IC, then this IC can drive the touch screen of a mobile or a laptop. This is a display IC, it can drive that screen. To make a complete system now, we proceed to the sixth stage, which is the final stage of electronic design, which is a product level design. So, this is the sixth stage, which is a complete system design. So, in the system design stage, we need multiple individual modules working together to perform a certain task. For example, we want to make a mobile handset, then we need typically a processor, we also need RFICs, we also need RF switches, we may need memory as well, we may also need screen driver. So, in system design stage, we bring multiple chips together because a chip generally solve only one application. So, for example, we have a IC which is a processor. So, it is generally able to perform functions on inputs. However, it may not be very good for transmitting the signal over the air, or it may not be suitable for driving a complete LED or LCD screen. So, we may need to have multiple ICs together to make a complete mobile handset. These, for example, these ICs, one of them can be a processor, RF integrated circuits, RF switches, these are generally different than the processor. We may need to have memory, we may need to have screen driver and many other ICs together. So, we take these ICs together, put them on a substrate which is called PCB or the printed circuit board. So, there is something called printed circuit board. This printed circuit board acts as a common substrate for all these ICs. On this PCB, we connect multiple ICs together, and in such a way we make the connection so that it makes a complete product. So, we can see how a PCB is turned into a complete product. So, for example, here we can see on the right side we have a PCB or called the printed circuit board. This PCB, this material is generally FR4. This green color laminate is FR4 laminate and this is called PCB. On this PCB we can see different black modules. These are nothing but the different ICs we put together, for example processor, RFICs, RF switches putting together to make a complete mobile. So in our mobile we may have memory as well, so we can put that ICs differently. So once we make this PCB, then the next thing is just to put this PCB on a plastic casing, something like this. This is a back cover, this is front glass screen, and so many other things we put together along with the battery, and we make a complete system which is a complete electronic system design. So these are all the 6 stages of any electronic system design, and these are very common to all the systems we take in the electronic industry. So this is how we design any electronic system right from the scratch, where we develop the device, to the final system design stage where we have a complete product. So this ends up our discussion on the electronic system design. Now we next discuss the second lecture, which is the circuit elements like R, L and C circuit elements. Basic circuit elements. So typically we have 3 elements, 3 passive elements actually. So MOSFET we will consider separately, which is active device. On the passive side we generally have resistor, which actually follows Ohm's law. Then we have capacitor, this works on energy storage in electric field. And then we have an inductor, which is based on the energy storage in magnetic fields. So there are basic circuit elements which we use to design any circuit in electronic system design. We have a resistor, which is a lumped component, it follows the Ohm's law. We use a capacitor. The capacitor we will discuss in the next slide. That capacitor is actually a device which stores energy in the electric field. There is a built-in electric field in the device which stores the energy. The third is the inductor. Inductor is nothing but a device which stores energy in the magnetic field. So there is a structure, specially designed structure, so that a magnetic field is confined in the device, and this magnetic field is storing the energy inside the device. So these are basic circuit elements. Along with them we have something called the voltage sources. like a battery, and then we have current sources. They provide constant current. So these circuit elements, these are very basic circuit elements which we use in our simulations. Voltage source is nothing but a ideal voltage source where we specify the value of voltage and this source provides that voltage. Current source is a constant current, whatever current we specify, that element provides that specified current. So let us talk about the resistor in detail. So the symbol of the resistance is shown something like this. This is the R, which is the value of this resistance. The current flows through this element from a positive terminal to a negative terminal, and the voltage V is developed across this element, which is V. If we plot the current versus voltage, the graph look something like this, which is a linear graph. So this is a current versus the voltage graph, and the slope of this line is V upon R, 1 upon R. Slope is 1 over R. R is the resistance of this, the value of this resistance. We need to note that all wires and circuit connections have resistance. Though we most often approximate them to 0. So here we see the symbol of a resistance, which is this zigzag symbol, and the current flows from positive to negative terminal, producing a voltage across the element. If we draw the I versus V graph, then the graph comes out to be linear and the slope of this line is 1 upon R. Here we need to understand that all wires, whatever we use in connecting two things together, all these wires, all these metals has certain amount of resistance, because these are made up of real elements. For example, we use silver or we use copper. All metals has certain resistance, smaller or bigger, but they have a non-zero resistance. However, when we simulate the circuits, when we put the circuits together in the SPICE program, we generally approximate it to 0, but for the actual simulations where we are very precise in simulation, we have to take care about these interconnections as well, because they are going to produce a certain amount of resistance when we fabricate them on the silicon on the chip. However, there will be a performance mismatch in the actual chip which comes out compared to what we simulated, because in the simulation we have not taken care of the contact resistance which is actually there in the chip. So, this is the resistance element. Next we discuss the capacitor. C. So, any two conductors A and B separated by an insulator. This forms a capacitor. So, let us see the symbol of the capacitor, which looks something like this. This is the symbol, and the actual structure is something like, we have two metallic plates, this is the first metal plate, and then we have the second metal plate below this. So, this is the second metal plate, this is A, and this is B, and between A and B we have a separation of length D. D is the separation between these two plates. So, here we have two conductive plates, and in between there is a dielectric, or if nothing is there then air act as a dielectric. These two metallic plate forms a structure which is called the capacitor. Now, if we apply a voltage across these two plates, there will be an electric field build up between A and B. That electric field will contain the energy which is stored inside the device. So, we have a voltage applied across it, VAB, between plate A and B, and there will be a current flowing inside this structure, and the potential is built up like this. So, this is the capacitor. Next element we consider is the inductor. So, inductors are the dual of capacitors. It means they store the energy in magnetic field. So, inductor is typically a coil-like structure. So, this is a symbol of inductor. When we apply a voltage across these two terminals, then there is a magnetic field build-up. There is a magnetic field build-up in this inductor. And this magnetic field is actually storing the energy. So, we can write the expression for capacitor and inductor so that we can compare both of them. So, for a capacitor, the expression between input and output is I, the current, is equal to C del V over del T, and for an inductor the voltage is equal to L into del I over del T. So, this is the input and output expression for a capacitor and inductor. In capacitor, the current is proportional to the del V upon del T, or the change in the voltage with time across its terminal, and proportionality sign we can remove by multiplying C, which is the capacitance of that capacitor, and this capacitance depends on the actual physical size of the element. Similarly, for an inductor, here the voltage is actually proportional to the change in the current across its terminal, V equal to L di by dt. Similarly, we can write the energy storage, how much energy is stored inside the capacitor and inductor. So, we have E, energy stored in case of capacitor, is half C V square, and in the case of inductor the energy is half L I square. So, half C V square is the amount of energy stored in the capacitor of capacitance C. V is the voltage applied across the capacitor. So, how much voltage we apply and how much is the capacitance of the capacitor, that dictates how much energy will be stored inside the capacitor. Similarly, for an inductor, energy stored is half L I square. L is the value of inductance and I is the current flowing in the device. So, how much is the current flowing, that dictates how much energy will be stored in the inductor. So, these are some basic circuit elements which we use inside our simulation programs to simulate our circuits. These are very basic elements. These are used to mimic various components. For example, we want to mimic a wire which is used to connect one module to another module. Physically, there is a metal which will be routed. So, this metal may have some certain resistance. So, we can mimic that wire, the actual connection, using resistance, and similarly capacitance and inductance can be used to mimic other behaviors. These are the circuit elements we generally use in the simulations of our circuits. So, this is all for today. Thank you.